So parametric equations. Literally named so because we're dealing with another parameter equation. Also a common mispronunciation of my last name. Parameter. Yeah, often actually.
How do you say it?
Parameter.
Oh, okay.
Yeah. So let's look at something. So one way to think about this, one way to think about a parametric equation, or I should say really a set, because usually parametric equations, you've got x as a function of t and y as a function of t, or x and y and z all as functions of some other parameter. Often t thought of as time, although it doesn't have to be that. There are certainly other parameters that are available to us, but t as time is usually the way we are thinking of it. Set of, sorry, lost my thought. One way to think about a set of parametric equations is tracking the motion of a particle in the xy plane or the xyz coordinate system. But for now, just the xy plane over time. So for example, we could have the parametric equations x equal to t plus 2 and y equal to t squared, where t is between -2 and 3. And so at a very basic level, you can just kind of see what's happening by plotting some points. So I could go over here and plot my x and y values based on what values t takes on. So t, I'm going to pick nice integer values. So t is going to be like -2, -1, 0, 1, 2, 3. X is just t plus 2, so I'm really just adding 2. So 0, 1, 2, 3, 4, 5. And y is just t squared, so 4, 1, 0, 1, 4, 9. So if I start plotting the x and y coordinates, let's see, I get 0, 4, 1, 1, 2, 0, 3, 1, 4, 4, and 5, 9. So it looks like this. And unlike, say, typically when I draw a graph, I'm not going to extend it with arrows in either direction because I've specifically said t between -2 and 3. I would, however, though, draw arrows indicating the direction that the particle travels as time moves forward. So if you want to, you can also draw little arrows and say, oh yeah, this is the direction of time increasing. Now, this is a pain to do, right? Like I usually don't want to have to do this, and I can see this definitely looks like a parabola. And I could often, not always, but often eliminate the parameter to see what the graph is going to look like. So what I could have done instead is I could have said, oh, well, if x equals, right over here, if x equals t plus 2, then t is equal to x minus 2. And I can plug that in for y and say y is going to equal x minus 2 squared. And then I have to be a little bit careful about my domain. I can see that since x is t plus 2 and t goes from -2 to 3, then x is going to be between 0 and 5. Which is exactly the piece of the graph I have. That parabola shifted 2 to the right from the parent graph, and then x going as far left as 0 and as far right as 5. So often one of the things we're asked to do with parametric equations is to graph it by eliminating the parameter. Like that, right? That's exactly. If someone said, find the graph of this thing by eliminating the parameter t, this is what they need for you to do.
And then you'd want to do like that graph or like the table how you did.
So like if I so like for example, let me give you another example. If I said to graph the parametric equations x equal to e to the t and y equal to e to the 2t, where t is greater than or equal to 0 by eliminating the parameter t. And relating x to y, essentially. So typically, I would say my go-to kind of process for doing this is to try to solve for t in terms of x. Because all things being equal, I would prefer to write y as a function of x. But that's usually what we do if we can. We could certainly, if it makes more sense, solve for t in terms of y and then write x as a function of y. That's just a little less what we're used to doing. Although we should be fairly comfortable at this point writing functions of y or functions of x. Because we've certainly done integrals where we've gone around, different axes and said x is a function of y or y is a function of x. So, but here, well, so here, I mean, okay, really, I wouldn't actually solve for t here. I'm going to show you how we could, but then I'll tell you what I really do. So if I was going to solve this for t, I'd say, okay, well, the natural log of x is equal to t. And then I'm going to plug that in for t here. So then y is equal to e to the 2 times the natural log of x, which is a terrible way to write that. I should simplify that as y equal to e to the natural log of x squared, which is really just y equal to x squared. And that's kind of the hardest way to do this. It'd be much, much easier if I was just a little observant. If I noted that y is equal to e to the 2t, which is really e to the t times e to the t, or if you prefer, e to the t squared, then it's really, really easy to see that x being equal to e to the t means y is equal to x squared. Much, much easier. So sometimes if you can see a thing, you should just try and see the thing. Now, I'm going to point out, I'm graphing y equal to x squared, but I'm not getting the entire graph. Right? So I'm going to show you this here. This is not the graph that I want. Because, well, first of all, t is greater than or equal to 0. So if t is greater than or equal to 0, what portion of the graph, or I should say, where does my graph start? Well, if t is 0, what's x? Yeah, what's y? Also 1. So really, starting at the point 1, 1 is going to give me that part of the graph. And this is the direction in which time increases. So here's time equal to 0, and here's time equal to bigger numbers. Now, interesting question. What if I had changed the domain of t? What if I had said instead, same parametric equations, x equals e to the t and y equals e to the 2t, but now t can be any real number. Do I get the whole graph then? I definitely don't. Let's think about it. If x is e to the t, what happens to e to the t as t goes to negative infinity? Well, if I think about the graph of e to the x, right, as we go down that way, it goes closer and closer to 0. It doesn't never get to 0 though, right?
Yeah.
So what we would actually get is if this was our parametric equation with those bounds for t, we would end up with the graph that almost started at the origin and then gave us all of this. T equals 0, 1, et cetera.
Is there a reason we don't draw an extra axis for t?
A what?
Is there a reason we don't draw an extra axis for t?
Well, we really, so again, this is why it makes sense to think of t as time. Because what we're saying is the particle that follows the path of this curve, in this case, this part of the parabola, right? The particle, as time increases, moves along this axis. But typically when we're graphing things, we don't plot time as a third. I mean, I know, so right, certainly sometimes we graph a function of time versus time, right, where time is on the x-axis and the function is on the y-axis. But if we have x and y defined in terms of time or some other parameter, we don't usually graph that parameter. It's not helping us see the relationship between x and y. That parameter is kind of like just a placeholder. It's there to help us kind of see how x and y are related to each other. And sometimes we can eliminate it. Sometimes we can't. Sometimes we just kind of stuck with it. Okay, fair question though. And just to kind of go along with this, so one more example of how the relationship might be the same, but the functions really matter. If instead my relationship was, say, x equal to sine of t and y equal to sine squared of t, where t is between 0 and pi, I'm still using the same relationship, right? I'm still getting, this is leading me to y equal to x squared. But now, sine of 0 is 0. Sine of pi is also 0. Oh, interesting. So what happens? Well, between 0 and pi, we hit pi over 2, and sine of pi over 2 is 1. So what we're going to do is, at time equals 0, we're going to get the point 0, 0. And then time equals 1, we're going to get the point, sorry, time equals pi over 2. We're going to get the point 1, 1. And then back again at time equals pi, we're going to end up back over here. So what we're doing here is our path is actually bidirectional, right? And when we go from 0 to pi over 2, we're going this way. And we come back down and then we go that way. And if you let time go on, you're just going to keep retracing this path, right? Because sine and cosine never get bigger than or equal to 1. I guess actually, if I let time go on, I would go back and get the other half of this. Right? I would go over to -1, 1, because certainly sine could be negative. Oh, you can't see them. Sine could be negative. Right? So if I went from, say, pi to 2 pi, I would trace out this little section over here and then come back that way. But that'd be it. And that's all of the parabola I would get if I define it this way. So you can still get the same Cartesian relationship, but your domain and range might differ depending on what x and y actually are as functions of your parameter t. Kind of interesting.
So, a whole point of this is basically like see how something or like a particle would move along.
Yeah, that is usually the way we most often think of it, because later on in 21D, we're gonna, well, not for you, but later on in 21D, when we start talking about like something in three-dimensional space, we're going to imagine it as like how this particle would move as time moves forward. It's not the only way, but it is often. Sure. Yeah, let's look at, so sometimes we often want to say find a parameterization. So find, and I should say before I say anything else, there's usually more than one right answer. So find a parameterization for the curves. Sorry, I got kind of. So for example, the line segment from 4, -2 to 1, 7. So it doesn't really matter how you want to do it, but when I think about this, if I'm going from and to, I usually like to say the place I'm starting at is my t equal to 0. And the place I'm ending at, it is usually, although not required, but it's usually convenient to say that we're ending here when time equals 1. It's just easy that way. So now if I draw this, I'm essentially starting over here at 4, -2. So it's really easy to write t when you say 2, or to write 2 when you say t. Right. 4, -2 when time equals 0, and then we're going to go over to 1, 7 when time equals 1. We just want this segment We don't want anything beyond those points. And we want to be going this way. So what's interesting here is you really don't have to like find the slope of the line at all. Not actually super helpful. So here's what I want. I want x, and I personally like to write x of t. Not required, but I like it. And y of t. And I know that at time 0, x should be 4 and y should be -2. And then when I plug in time equal to 1, I'm going to want x to be +1. So if I'm plugging in time equal to 1, I want to end up subtracting 3. Right? Because I'm literally moving 1, 2, 3 spaces back in the x direction. So I'm going to subtract 3 times time. When time equals 0, I'm still going to get 4. And when time equals 1, I'm going to get 1 as desired. Similarly for y, if I'm going from -2 to 7, I'm increasing by how much? Right, so I'm going to add 9t. Very straightforward. Parameterizing a line segment is usually pretty easy. Now, is it the only answer? Definitely not. You could have just as easily, well, maybe not just as easily, but almost as easily said, I'm going to go from time equals 0 to time equals 2, just to be weird, and then say x of t is equal to 4 minus 3/2 t, and y of t is equal to -2 plus 9/2 t. And that parameterizes the same line segment in a slightly different way. It's convoluted a little bit, but if someone, the reason I bring this up specifically is because this quarter I've seen in 21D, one of the professors asked students to find different parameterizations of the same segment or curve. And so this is one easy way to get there.
And this might sound really stupid, but is there a line connecting any point on the plane that's straight?
Yes.
Okay.
Yeah, any 2 points on a plane can always be connected by a straight line or a line segment.
Okay. This works for any 2 points.
Yep. Yeah. Yeah. And so literally, you can take any 2 points, take your 0, just say x and y equal that point first as just your constant, and then add the multiple of t that is just how far the x coordinate is from the x coordinate and the y coordinate is from the y coordinate. It's very, very straightforward. Sure. Let's look at another harder example. And so I should have said, right, here's my parameterization with t between 0 and 1. When you parameterize something, you do have to specify the bounds for t. Cool. Let's look at something a little bit harder. Let's say we want the portion of the parabola y equal to x squared minus 2x minus 8 below the x-axis. So it might feel kind of lame, but if they give you y as a function of x, there's always a really, really easy parameterization, or x is a function of y. Your parameterization can just be x equal to t, y equal to t squared minus 2t minus 8. That parameterization is always available to you if you have y as a function of x. But then we have to describe how low and how high t go. So if I want to be below the x-axis, I'm essentially trying to find, right? I know my parabola looks something, actually don't, it looks something like this. And I've got some x value here and some x value here. So I have to find what those are to actually find my bounds for t, which is not hard. We know how to factor this. X squared minus 2x minus 8 equal to 0. Factors as x minus 4 times x plus 2 equal to 0. So this is going to be where x equals -2. That's going to be where x equals +4. So our bounds for t, since x is equal to t, are going to be the same as that. So we're going to go as far down as t equal to -2 and as far up as t equal to +4. Wow, why do I my brain's not working? I meant to write 4, not 2. Okay. Yeah, cool. I want to go that way. I kind of want to go the other way. No, fine. Sure. How about the left half of a circle? a circle of radius 3. Sure. Circle of radius 3, center at the origin. Also, we're going to describe the direction as well, starting at the point 0, 3 and ending at 0, -3. Going, well, the only way you could go if it's the left half of the circle is by going counterclockwise. Let's draw it. Starting here, we're ending here, and we are definitely going this way. And for me, I would imagine that where I'm starting, usually, unless there's a really, really good reason not to, like in this previous example, usually where we're starting is going to be where time is equal to 0. All right, so it might be helpful if I knew the equation of this circle or this half circle. It's what, x squared plus y squared equals 9. So, circles. Excuse me. Usually, when we're trying to parameterize a circle, it almost always boils down to x being something with sine or cosine and y being the other one. Usually we think of x being cosine of t and y being sine of t, but actually either one will work depending on where you want to start. So, in fact, yeah. So I've kind of set myself up for failure the way I've started this. So I'm gonna change my answer a little bit, but you'll see. So all things being equal, usually when you go around a circle, right, we usually go in the counterclockwise direction where the angle increases. So we might think of this, well, usually we're just thinking of x as 3 cosine of t and y is 3 sine of t. But then if I wanted to get this portion of the circle, I'm not going to be starting at t equals 0 because up here the angle is pi over 2. So I'm starting at t equals pi over 2 and going counterclockwise, I'm ending at t equal to 3 pi over 2. That is one way we could describe this left half of the circle of radius 3. Now I should point out that these parametric equations for x and y totally satisfy this equation. If you plug in 3 cosine for x and 3 sine for y, 3 cosine quantity squared is 9 cosine squared plus 9 sine squared equals 9 times 12, which is 9. Now, if you wanted to be fancy about it, you could try to do it so you could start at 0. So if I actually wanted to start at 0, well, I want the x coordinate to be 0. I know that sine of 0 is 0. And I want the y coordinate to be 3. And I know that cosine of 0 is 1. So I could alternatively say, I'm going to let x equal 3 sine of t and y equal to 3 cosine of t. Now, this might not be exactly right, but I'm going to fix it if it's not. So, does this start at the right point when time equals 0? Yeah, in fact, let's be smart. Let's make a little thing. So when time is 0, x is 0, y is 3. Great. Now, if I'm going from 0 and I'm getting bigger, I'm imagining this is going to be pi down here. Let's see. When time is pi, sine of pi is also 0. Cosine of pi is -3. Or -1, but then times 2. So my beginning and my ending are right, but am I actually going to the points I want? Well, let's pick a point in between 0 and pi, like pi over 2. Uh-oh. Sine of pi over 2 is 1. 3 times 1 is 3. But I need my x coordinate to be what? -3. Okay, it's easy to fix. I fixed it. Yeah, I fixed it. So this is another, you don't have to do this. So the thing is, any parameterization that you come up with that's right is right. But there's almost always more than one way to do it. Well, truthfully, there's probably technically an infinite number of ways you could actually answer this question. Because instead of doing this, I could have said, well, I'm going to do -3 sine of t over 2 and 3 cosine of t over 2, and then let t go from 0 to 2 pi. So there's almost always another way you can do it.
How would you approach this if circle wasn't centered?
Annoyingly.
Yeah, that's what we were doing in class.
Okay. We'll get there. We'll get there in a minute. Yeah. So what I will say is usually you're not, well, I don't say, I feel like usually you're not asked to start with the circle and parameterize. Usually you're starting with the parameterization and then asked to kind of see what it looks like. Not that you can't do both. I just feel like more of the questions I've seen are kind of starting with some parameterization. So for example, yeah, not yet. We're not there yet. So for example, someone might give you the following parameterization. X equal to given a parameterization. Again, we're back to describing the curve. And specifically, I want to talk about circles. And well, I want to talk about sine and cosine. That was what I see generally what I'm saying. So if we have something like this, x equal to 4 cosine of t, y equal to 4 sine of t, and t is going from 0 to, sure, let's just go all the way around. Here is what I recommend in general. Although I will say, this is taking me a fair amount of time to kind of come up with this. Not like I sat down, but like over the years, I'm like, oh yeah, this makes sense. So here's what I would recommend doing typically. First, you need to have just cosine and just sine for x and y. Like one can be sine, one can be cosine, doesn't matter which, but you don't want like other things in there, right? You don't like cosine squared or cosine plus sine, that's problematic. I'm just saying if x equals something times cosine or something times sine, and y equals something times the other one. Isolate cosine and sine, meaning I'm going to say that cosine of t equals x over 4, and sine of t equals y over 4. This might feel like too much work for this particular problem, but there is a method to this madness. So then I know that cosine of an angle squared plus sine of the same angle, the angles do need to be the same, squared is going to equal 1. So I can say, great, cosine squared of t plus sine squared of t is equal to 1. But then I can replace cosine squared and sine squared with what they're equal to. So cosine is equal to x over 4 squared. Sine is equal to y over 4 squared. That's equal to 1. And then you could leave it like that. You could totally leave this as x squared over 16 plus y squared over 16 equals 1. But the more standard way of writing it would be to say x squared plus y squared equals 16. So this is totally circle, radius 4, center of the origin. So we have a circle, and we have the full circle of radius equal to 4, center of the origin. Now, the reason I mention this is because sometimes you have something slightly different. Here's what I mean. What if instead I was given the less nice parametric equations, x equal to 3 sine of 2t, y equal to 4 cosine of 2t. And t is going from 0 to pi. I should point out, by the way, that sometimes we might ask about the direction here. The direction here is just counterclockwise. And if you're not sure how to find the direction, and I should say, if you and myself included are not sure how to find the direction, usually what we do is you just start plotting some points. So for example, if I was trying to figure out the direction I was traveling along the circle, I'd be like, okay, well, I'm starting there. And then I'm just going to plug in the next like convenient value of my angle t. So I plug in pi over 2. Cosine of pi over 2 is 0, sine of pi over 2 is 1, so I'm at the point 0, 4. So I've definitely moved over to here at time equals pi over 2. So I'm definitely moving in this counterclockwise direction. That's how I find it. That's really the only way I'm aware of that you can. There's no like way you can just look at it and tell. You have to plug in points to really tell the direction typically. Now what about this thing? This is where what I just said I think is more applicable, right? Here, you totally feel like, yeah, I know it's a circle of radius. Center of the origin. But here, doing what we just did is actually really useful. So I'm going to say that x over 3 is equal to sine of 2t, and y over 3 is equal to cosine of 2t. And as long as the angles match, which they do, we're good to go. So then we can take this and say, great, sine squared of 2t plus cosine squared of 2t equals 1. But then replace each thing with what it's equal to. So really what I have here is x over 3 squared plus, sorry, oops, I lost the 4. That's kind of important. That should have been y over 4, not y over 3. Plus y over 4 squared equals 1. Which people might rewrite as x squared over 9 plus y squared over 16 equal to 1. And that, my friends, is not a circle. It's an ellipse. Let's graph some of the points.
Wait, what if you just multiply the 9 over the 16?
Totally. So if I multiply everything by 9 and by 16, then I'm going to get, let's see, the 9s will cancel. We'll have a 16x squared plus a 9y squared equals 144. Because really what I did was I multiplied everything by 144. And 144 over 9 is 16, 144 over 16 is 9. Still an ellipse. So here's the general kind of thing to know. If you have x squared plus y squared, if the coefficients are the same, you've got a circle. If the coefficients are different, you've got an ellipse. It's like there's a word I'm looking for. Well, no, it looks, I mean, it's kind of like an egg, except it's like, you know, an ellipse. So, but here's what I really do. I'm just going to plot the intercepts. So if I set y equal to 0, x could be positive or negative 3. 3 over 3 is 1. Negative 3 over 3 is negative 1, but squared is still positive 1. So my x-intercepts are plus or minus 3. And similarly, my y-intercepts are plus or minus 4. And this ellipse is kind of elongated along the y-axis a little bit. Pretty good drawing. So there's my not very, oh God, like the I want to say like demorphed. There's the word I can't find. It's like where I've done something to this graph. I've taken the circle and I have, but there's a better word. I have deformed. Thank you. I've deformed this. It's a deformed circle. Good God. Yeah, I think I'm missing. Yeah, I'm like demorphed is not what I want. Okay. Yeah. Could we get a hyperbola in parametric equation? Yeah. In fact, hyperbola, yes. So here's what I would say. Oh, yeah. Yeah. Totally. It's weird though. So yeah, it really comes from the hyperbolic trig functions. So it's kind of funky, but I will point out that, so really you could think of a circle, right? When we think of a circle, usually we think of this angle as being theta, but I'm gonna call it t. Right, this point on the circle, if it's a circle of radius 1, is the point cosine of t, comma sine of t. And then, right, the equation of the circle is x squared plus y squared equal to 1, and then the cosine goes in for x, the sine goes in for y, and you get the usual trig identity, cosine squared t plus sine squared t equal to 1. Well, similar thing is true for a hyperbola. So let me graph you kind of the easiest hyperbola, which is x squared minus y squared equal to 1. Which I'm not great at graphing hyperbola. So you've got x-intercepts at 1 and negative 1. I will also point out that this hyperbola, like all hyperbolas, has a slant asymptote. Actually, has 2 slant asymptotes. And here it's going to be y equals x and y equals x. So here are my slant asymptotes. We'll try to draw kind of nicely here. Cool. And then basically, right, as the y values get bigger, the x values get bigger. So for example, if y was 1, x is going to be root 2, plus or minus root 2. Yeah. So if y was 1, x would be plus or minus root 2, which is like 1.4. So what happens here is this just goes like this. Not my favorite. Not good with hyperbolas. Sorry. Symmetry, maybe. Yeah, okay. So hyperbola is great. X squared minus y squared equals 1. And there's something really kind of cool, which I've kind of forgotten, to be honest. But there is an identity here. There's a hyperbolic trig identity. So I know, actually, I don't know. Did I briefly talk about the hyperbolic trig functions? I may or may not have. I might not have. So let me remind you just briefly. Hyperbolic sine is not a trig function at all. It's e to the t minus e to the negative t over 2. And hyperbolic cosine is e to the t plus e to the negative t over 2. And these hyperbolic trig functions are called hyperbolic for a reason. Just like this point on this curve is the cosine of this angle, comma the sine of this angle, the point on this curve here, if you, and this gets kind of funky. So really, not only is this angle equal to theta, this actual whole, yeah. Sorry, I have to think for a second here. The area of this sector is theta, right? Or t, right? This whole area, right? Because the area of a sector is 1/2 pi times, or 1/2 the angle times the radius squared. Sorry, so let's see. So the area of the sector is 1/2 t times the, so sorry, 1/2 the angle. Apologies. Yep. Think about the area of the whole circle. It's the area of the whole circle. Fine. Or 1/2 times 2 pi times r squared.
I always thought it was the r times the angle. How does it do?
So wait, I'm talking about the area of the sector, not the length of the arc.
Okay, yeah.
The length of the arc is r times theta. The area of the sector is 1/2 times the angle times r squared. Which in this case, r squared is just 1, so it's really just equal to 1/2 t. And fun fact, this point here, if we call this area here t, this point here is the hyperbolic cosine of t, hyperbolic sine of t. I might be off on that a little bit. I might be off by a factor of 2. I'm not gonna lie. But you can see this more easily by just knowing the following. There is a hyperbolic trig identity. Just like cosine squared t plus sine squared t equals 1, hyperbolic cosine, hyperbolic cosine squared t minus hyperbolic sine squared t equals 1. And so if x equals hyperbolic cosine and y equals hyperbolic sine, it exactly parameterizes a hyperbola.
So two things. One is, did they look at the graph and then try to come up with a function, and that's how quotients seem to develop?
I don't know. I don't know how this came out. I do know that for these hyperbolic trig functions, at least the reason I think we call them hyperbolic trig functions is because they have a lot of similar behavior to the actual trig functions. Specifically, where they evaluated 0, hyperbolic sine of 0 is also 0, hyperbolic cosine of 0 is also 1, and how their derivatives behave. The derivative of the hyperbolic sine is hyperbolic cosine. The derivative of the hyperbolic cosine is the hyperbolic sine. It is positive, not negative. So it's not exactly the same, but it's close to the same. And then we define the other hyperbolic trig functions the same way. Hyperbolic tangent is just that divided by that, which is e to the t minus e to the negative t over e to the t plus e to the negative t. It's not super important, but you asked the question and I had an answer. So
yeah, so is is hyperbolic tangent also on that graph somehow? Like the same way that,
Well, maybe, yes, like you could probably do the thing where like you draw the thing, but like, I don't know. Probably, but we're not gonna get into it. So, cool, but let's move on. So the thing I would say is that if you've got X and Y equal to sine slash cosine and the other one, usually it pays to isolate the sine and the cosine and then square both of them, add them together to see what you've got.
So X doesn't always have to be cosine, it could be sine.
Right, X could totally be sine.
Okay.
Usually we default to making it cosine, but it's totally possible that X could be sine and Y could be cosine, and you still have a circle. Or maybe an ellipse, if the coefficients are different.
so long as it's a circle, it doesn't matter which is which, right?
It matters in depending on what your domain for T is, it'll change where you start. Right? If you have back to the right, well, like back to this previous example, if I was doing this version, X equals 3 cosine T, Y equals 3 sine T, and I started at T equals 0, that would have started over here. Whereas if I write and then gone counterclockwise. Whereas if I do it this way, X equal to negative 3 sine T, Y equal to 3 cosine T, and I start at time equals 0, that's going to start me up here. They still describe the same circle, they just start at a different point and end at a different point based on the same T value. You would ask about a circle not centered at the origin.
But here's the thing, I think, okay, yeah, we did that, and it was like, we were trying to find, like, it was like move this.
Were we given the equation of the circle and asked to find the parameterization, or vice versa?
I think it was just like, let me check.
Okay.
I'll watch it next time.
Okay.
Thank you, though.
You're welcome.
Next week, Jen.
See you next week. The last week.
Oh, yeah, so it's like. I'm not exactly sure
Okay.
if this is actually, this might not be parametric. I think it might be something else, because it's like a wheel of radius rules of wheel.
Oh, yeah, that's something totally different. Yeah. It's not the cycloid.
Okay.
That's something totally different.
We did it in this thing, and then we
Sure.
were calculating the parametric curves right after that.
Right.
Okay, that's what I got.
It is possible to deal with a circle not centered at the origin.
Yeah.
Um,
And we were looking at like, how you have dy over dx and then you have d squared y.
right. So that's actually where we were about to move to is talking about how to do calculus with parametric equations.
Yeah, that.
So let's say, yeah, we have enough time. So let's say we have the curve x equal to t squared and y equal to t cubed minus 3t. And t is any real number. And it's certainly possible to solve for x in terms, like you could say t equals the square root of x and then plug that in there. But it's a little dicey. Like really, if you wanted to, you could say t equals plus or minus the square root of x. And then if you plug that in there, you're gonna get y equal to plus or minus the square root of x cubed minus 3 times plus or minus the square root of x. Right, it's a little funky. Right, if you really want to, you could factor out a plus or minus root x, and then say y equals plus or minus root x times plus or minus root x squared, right? Because the factor one out is just x, and then minus 3x. But graphing that's just a little funky, right? Like we could try to graph it. So if x equals 0, y is going to be 0. If x equals 1, y is going to be plus or minus 1 times 1 minus 3. So plus or minus negative 2. So when x is 1, y could be 2 or negative 2. But if I'm going to do it, I mean, it's just as easy at this point to be like, well, let's just make a table. Oops. T, right? T could be 0, I think, plus or minus 1, plus or minus 2, plus or minus 3. So t is 0, x is 0, y is 0. T is 1, x is 1, y is 1 minus 3, which is -2, and t is -1, x is still 1, but y is now -1 plus 3, which is +2. And then similarly, plus or minus 2, x is going to be 4. If x is +2, then, or sorry, if t is +2, then y is going to be 8 minus 6, which is +2. And if t is -2, y is going to be -8 plus 6, which is -2. And we plug in 3, x is going to be 9, y is going to be 27 minus 9, which is 18, or -18. Okay. So
basically, are we then using, I can't even say it, parametric, when this situation happens, when you just like can't really graph it, it's like plus or minus?
can't really graph it, or it's not that we couldn't, but where we might not be able to in another example, or just the pain to try and solve for y in terms of x. Like maybe you could, if with a lot of effort, solve for y in terms of x, but you might as well just use this other thing that's easier to do. So looking at what this graph looks like though, let's see. So you got 1, 2, 3, 4. So x is 0, y is 0, x is 1, y is 2, x is 4, and y is plus or minus 2 again. So let's see what happens. So when x is 0, when time is 0, I'm right here. And then when time is 1, x is 1 and y is -2. So I'm going this way. And then when time is 2, x is 4 and y is +2. So then I'm up over here. So looks like I'm going to do something like, yeah, sorry, I need to think for a second. Oh yeah, see. Sure. Sorry, it's
That's so confusing.
I know. Yeah, that's interesting. I should look. X is 3. Okay, sure. That does go there. And then kind of goes this way. That.
Oh, okay. Well,
So here's time equal to -2, time equal to -1, time 0, 1, time equal to 2. Yeah, and so just to point out, the way I found the x-intercept there in my head, without showing you the work, was I said, well, x-intercepts, how do we usually find x-intercepts?
that when like the y is equal to 0.
Right. So if I said t cubed minus 3t equal to 0, I'm going to get t times t squared minus 3 equal to 0. So either t equals 0, great, we found that one, or t equals the plus or minus the square root of 3. And if t is plus or minus √3, then x is going to be plus or minus √3 squared, which is just 3, which is exactly right there. So that's how I found it without showing the work. And then just to start off the process, how do we find, say, like a horizontal tangent? Well, how do we usually find a horizontal tangent?
I forgot.
So horizontal lines have what kind of slope?
0.
Right. So we're going to set dy dx equal to 0. But here's the thing. dy dx is equal to dy dt over dx dt. So using our parametric equations, dy dt is just 3t squared minus 3. Dx dt is 2t. And then if I set this equal to 0, as long as the denominator isn't 0, I'm just setting the top equal to 0. So I'm going to say, well, that's where 3t squared minus 3 equals 0. So t squared equals 1. So t equals plus or minus 1. Which makes sense because those are totally right. Well, at least if you look at my graph, where t equals 1 and -1, it definitely looks like we have some horizontal tangents. But the bigger piece of information here is, yeah, when you're finding dy dx, it's really just dy dt divided by dy dx. Or sorry, dx dt, apologies. It's kind of interesting. You can totally think about the derivatives canceling. here's,
Yeah, that's what someone asked.
right.
Yeah.
So you can think, so we say this a lot, they're not fractions.
Yeah.
But in any way, shape, or form that you would like for them to act like fractions, they do.
Cause you could write that as like, instead of it's like dy dx, it could be like f of x.
Right,
prime,
right.
you
So let me actually kind of show you the idea here. So really, y is a function of x, right? So y is equal to some function of x. But really, x is a function of t. And so is y. So really, that's some function of x of t. And so if I want to find dy dt, I'm just going to use the chain rule. I'm going to take the derivative of this, it's going to be f prime of x of t times x prime of t. But using my other notation, f prime of x of t, well, f is just y, right? So this is like I took the derivative of y with respect to x. And x prime of t is like I took the derivative of x with respect to t. And if I want to solve for this, that's really the trickery that's happening here. Really, this, it's not that the division works the way it works, although it looks like it, it's that we're manipulating the chain rule.
That's weird because like, it's like the dt from the dx goes to the dy. And that would be, like, the cross.
But if you look at this here, this is the chain rule, and this is why we like writing the chain rule like this. Because although you don't have to, and technically we shouldn't, you could think of the dx as canceling here, and then the right side is dy dt, the left side is, oh yeah, they're equal. That is literally one of the reasons we like to write it that way. But then you can totally divide both sides by whatever and get that over there. So that's where that's coming from. It's coming from the chain rule.
Yeah.
But in practice, we're just like, oh yeah, dy dx is dy dt over dx dt. Now, unfortunately, it doesn't work the same way for second derivatives. I will just point out, and then I'll stop.
Then why do we use the second derivatives in this?
Well, because sometimes we care about this. Sometimes we want, like, I want to know what's the concavity of this function. So the way you find the second derivative is you take the derivative of the first derivative. Right? And now I'm just going to call this y prime for a second. So I'm really finding dy prime dx. Right? And then I'm going to use the same trick. Dy dx is dy dt over dx dt. So dy prime dx is dy prime dt over dx dt. But then, here's where it gets nasty. The bottom is dx dt, and the top is the derivative of y prime. But y prime is dy dt over dx dt. So you have to take whatever you had from before and plug that in here.
What you had from the first.
Right, but you've already done that. So it's not like you're actually just calculating. You're just taking, so basically in this particular example, it would end up being the derivative of 3t squared minus 3 over 2t, which I would probably simplify before differentiating, over dx dt again. So I would rewrite this as the derivative of 3t squared over 2t is 3 halves t, minus 3 over 2t is minus 3 halves times 1 over t. And dx dt is just 2t. I've already done it. So then the derivative up here is going to be 3 halves minus 3 halves times negative 1 over t squared, right? That's t to the negative 1. All over 2t. And then you can do some simplifying. So it's kind of a pain, but yeah. Second derivative is not quite, it's not just like second derivative over second derivative.
Yeah.
Yeah.
Thank you.
You're welcome. We'll talk more about this next week.